Hi, in this series we're looking at the wonderful world of shaders. In this episode we're going to implement a wireframe shader so that at runtime you can switch between your rendered model and that of a wireframe. Let's get started. Here we have a windmill for a tile-based project I'm working on. The assets are from the K-Kit Medieval Builder Pack, and I put a link in the description if you want to go check out her awesome work. I was looking for a building effect that didn't require you to have several different models for each stage of building. So my idea was that when the model is building, you show the wireframe and then you fill in parts of it over time, like this. Or maybe you just want to show the wireframe like this, for when you're placing or moving a building. So how are we going to do this? Let's think about how this works in reality. When you're rendering an image, you process each triangle in turn in the fragment shader. So let's consider a solitary triangle for now. Each vertex of the triangle has a coordinate in the world and a UV coordinate for the texture mapping. Let's assume the triangle is visible, then in our fragment shader, each pixel is going to be found by interpolating between the UV coordinates of each vertex and the texture to find the required pixel value. We can use something similar for creating a wireframe effect. What we really want to do is colour in the pixels along the three edges in these areas and leave the centre transparent. We can use the Barycentric coordinate system to help us find out how close we are to an edge. The way this works is by assigning each vertex a value from 100, 010 and 001. Then for any pixel in the triangle, we can interpolate between this coordinate system to find if we are close to an edge. So you can consider this as three axes that come out of the vertices and head towards the edge opposite, where the value is 1 at the vertex and 0 at the edge, for each of the three coordinates. For example, this pixel would be a half, half, and 0.1. So given the pixel coordinates, we can say if any of the three components are within some threshold of the edge, then we colour that in, else we'll leave it transparent. This will effectively draw our wireframe for us. One consequence of this method is that you'll get double thickness for the lines where the triangles join, but single thickness at the edges. However, as most edges are internal to a mesh, this will not be very noticeable. We will start with a standard unlit shader. The first thing you'll want to change is the render queue this is executed in. As we're wanting to use transparency, we set the queue to transparent, and the blend mode to source alpha 1 - source alpha, so it knows how to interpolate between our transparent colour and those behind. In our properties menu, we'll add variables for our wireframe colour, both for the forwards and backwards facing triangles, and for the width. We're going to need two passes to accomplish the wireframe shader, one where we create the wireframe for the forward facing triangles and one for the backward facing ones. These will be more or less identical, so I'll just show the process for the forward facing ones and you can look in the code for the rear facing ones. We focus on the forward facing triangles by using callback to remove the backwards facing ones. Our hashpragma lines define each of the functions we're going to implement. The fragment shader is where we'll do our colouring of the triangles. We don't need to alter the vertex function at all. We do need to add a custom geometry function as we want to add the barycentric coordinates into each of our triangles. We define it with a hashpragma line just like the others. For the G2F geometry struct, in addition to the position, we need to add the extra float3 barycentric. We're going to assign this to text coord 0 because you have to assign it to something, and we'll fill it in the geometry function. The geometry function is going to proceed a triangle at a time, each of which has 3 vertices. For each triangle, we pass through the position of the vertices, which is what the default geometry function would do, but we also want to populate our barycentric variable. It doesn't matter which order you specify them, so long as they're each different. Now the fragment shader is where all the fun will happen. This runs for each pixel. What we want to do is make the output white if we're close to the edge, or transparent if not. We know that the coordinate value on the edge is 0, so we can just take the minimum of our 3 coordinates. Any of them are within the threshold, say 0.1, then we're near an edge and we can colour it in. This ends up looking like this on our model. On a simple model like a sphere, where the triangles are all the same size, this works fine. However, on our windmill, it doesn't look so great. And whilst the cube is consistent with itself, it's different to the others. This is because we're defining an edge based on proportion, so the bigger triangles will end up with thicker edges. Maybe this might be something you want, but I certainly don't. So what we need is a way to normalize this based on the triangle size. We need to know the rate of change of our barycentric value as we move through the pixels in the triangle. HLSL have two base functions that do this for you, ddx and ddy. These calculate the difference between two pixels in each of the horizontal x and vertical y directions. To combine them, we can just sum the absolute values of them. This is exactly what the fwidth function in HLSL does for us. With this fwidth function, we get essentially the unit of change for the given triangle. Now we use the step function, which operates on each of the elements of the float 3 individually, returning 0 if the barycentric coordinate is within our threshold. The threshold being the unit width multiplied by our desired wireframe width. We just need one value for the pixel, so we take the minimum of each 3, which will give us 0 if we want to colour this in. So we just invert that for our alpha value. Now you can see we have a constant thickness across our windmill, and this matches up with the sphere and the cube also. There is no anti-aliasing on our wireframe though, so the edges can look quite jagged. What we want to do is blur the edge a little bit. For this, we can use the smooth step function. This returns 0 if the value is less than the minimum, 1 if it's greater than the maximum, and it's interpolated between the 2 points in between. Now that your edge fades out, you might want to scale it up a bit to retain roughly the same sized edge. So back on our models, we have the non-alias version. Now we can apply the new version to the windmill, sphere, and cube. This looks so much better. The smoothing happens between the edge and the centre of the triangle. Most lines look smooth in both directions because you get a contribution from two triangles. The exception is on the edge of the models where it's only going one way. There is no easy way to fix this, so it's just something we're going to live with. My windmill model is created from 7 submeshes, one for each of the coloured parts. So all I do for my animation when I hit build is I start with the wireframe shader on everything, then replace the wireframe shader with the required material after some time step. As ever, the full code is linked in the description below, and I hope you found this information useful in some way. See you next time.